Thank you. Yeah, so as Oksana said, so the goal today is to share some feedback from the LHCb collaboration and share how different analyzers are making use of all of the great Python tools that are available in the ecosystem. So to first start, I want to highlight a bit the data workflow within the LHCb collaboration. So here from our trigger and offline processing, we have a bunch of different steps, and this relates to quite a large infrastructure for the data processing, where it is primarily built on C++ backend. However, it makes use of a lot of Python steering for option files, for different calling of the different C++ classes, all of these sort of things, running the algorithms, defining the algorithm order, all of these sort of things are steered with Python and is made a lot more readable and user-friendly to have this Python steering. And additionally, there are still many tools available with the ability to complement the structure. Things like doing checks, doing tests, all of these sort of things on the different steps to make sure the process is working the way that we expect it to. So the tools, though, in today's discussion are going to focus primarily on the last two stages, which is our analysis productions, and then finally, afterwards, the user analysis, where people are actually doing their physics. And so again, the goal today will be a little bit different from some of the great talks that we've already seen at PyHEP, is to share the Python tools and the experience of the analyzers from the LHCb collaboration, not so much a hands-on experience, but what people are doing, how they're using it, and what areas that have some holes or what areas are working great. And we want to share our feedback to the Python community. Okay, so moving on then to slide 3, we have our analysis in the LHCb. So for our data format, the LHCb analyses primarily use flat n-tuples, so your standard root files outside of the physics application stack. Additionally, there is a filtering of these samples to create the n-tuples, and this is done with individual grid jobs in the past. And now moving towards the LHC run 3, this is looking to be centralized. Additionally, people are making use of snakemake, and so this is utilized to create reproducible and scalable analyses. And if you're not familiar with snakemake, it is a build system entirely based in Python, which allows analyzers to basically rerun their analyses and make sure things are happening in the same order that you would expect it, and allows for cross checks between different users. Additionally, in the same sense, people are also making use of GitLab CI to do a very sort of similar thing. So not just unit tests and things that you normally would associate with a continuous integration of your Git system, but allowing some reprocessing and reproducibility of analyses by running it through with the GitLab CI tools. However, there are some concerns with the data access and caching of the different stages with this. And for people familiar with LHC experiments, there's a lot of data to deal with. So this can become troublesome, and people are working on ways to get past this. Additionally, now the collaboration makes use of software environments, and they make the use of these environments to run the analyses so that people are trying to work in the same nutshell. In the past, on interactive clusters, there was the abuse of physics application environments and using central CERN building blocks like from LCG. But then locally, you had users that had much more ad hoc builds, some homebrew things where they've made their own tweaks, and then maybe some system package managers where you can get to a specific version or these sort of things. But across the board, there was a lot of room for differences. So now moving towards run 3 and beyond, on our clusters, we want to employ version conda environments installed on CVMFS. And these then will be centrally managed so that people are getting access to the same software stack. And then locally, we can make use of Conda or Mamba with Conda Forge so that people can check out the same software and make sure that when they're using these different packages available, that they're using the same thing as the other ones that they're working on the analysis with. Okay, so now I want to move to the analysis productions within LHCb. So what analysis productions are is a centralized sample filtering to create manageable n tuples for the analyzers to use, to go from your 2 terabytes of data that you initially have after the trigger and maybe some skimming, to now down to something that's smaller and able to be used, maybe order of 50 gigabytes, where people can have these locally and make use of it. And so for this process, some of the tools that are made used is Uproot. And so as has probably been discussed over and over through the Python community, Uproot is an input-output for root files, and it shows better performance than root's own file IO methods, and allows, additionally, what's great about this is it allows to read the data straight into arrays, data frames, these sort of things that people can then make use of the other nice Python tools available. And then following up on that, we have Awkward, NumPy, and Pandas, which are used and allows for the physics tool manipulation handling before shipping the output to the n tuples. And this is flexible use with Uproot, and it has the additional nice flexibility for developers where you can change between the different formats during development. So if one person wants to use NumPy, somebody else wants to use Pandas, you can make use of using these different things, all while staying with the Uproot package and then shipping off things to the output n tuples in the end. Some feedback given from the analysis production groups. So they've seen a significant improvement in the reading of files with the Pythonic tools. And this then leads to a very huge performance boost when you're handling many files like they are at the production level. Additionally, Pythonic data frame structures integrate more nicely into other libraries rather than using Root's custom version, where often the Python libraries talk and communicate with each other better than trying to use a root library that's been developed mainly with C++ in mind, and then trying to adapt this to Python and the other available Python libraries. So having something that is more compact and working together with each other is great. However, there is still some missing functionalities. For example, JSON serialization for the HIS package. But some of these things can be manually implemented reasonably. And because it's Python and people are very handy in developing here, filling in some of these holes isn't too bad. And then here now at the final point, and you'll notice a running theme through the talk, lack of documentation in some libraries makes things difficult. And what then happens is you need to have expert understanding to trawl the source code to make sure that you can figure out what's going on and then how you can put things together. And oftentimes when you have many users in a large collaboration, this can be difficult for younger students as they're trying to get into things and make use of these packages. So I'll probably say this on almost every single slide throughout this talk, but improvement in availability of documentation is the way to go. Okay, now I want to diverge farther down the line, moving towards our analyses. And first I want to highlight an LACB publication, so a prompt charge particle production paper, which was done solely using the scikit-hep tools. So basically everything after the data processing was all performed with the Python HEP tools available. They made use of Uproot for interfacing with the input root files. They made use of boost histogram to fill the role of your classic root histogram classes. And the bonus here was the functionality and user-friendly availability of the multidimensional histograms within boost histogram. Now, one might be thinking, okay, we say multidimensional histograms, but what do you actually mean here? Because I just show 2D plots. But what you're actually able to do then is additionally, you'll see that you have a differential distribution within ADA. So you have a binning of the ADA distribution going from 2 to 4.8, and you can have 6 different bins there. And then additionally, you can have some maybe binning on your PDG ID to get the different channels or these sort of things. So now you're up to a 4-dimensional histogram where you can store all of the information that you want to plot down the line in the future. And you can carry it along in one Python object, which is really handy. It compacts things and is really, really nice to use. Okay, and then moving on now to the fitting side, makes use of iMinWe, which is a user-friendly interface to MinWe2 to process the minimization. And then the PDF for the analysis was built in Python using the various SciPy library components to put this thing together. Now, some feedback from the analysis group. So what's great is the standard scientific Python stack can handle a good portion of the analysis flow. However, there are still some cases for people to try and find a splash from other HEP tools when all of the things aren't quite readily available, or if the exposure to some tools is missing. Additionally, then Python tools often are more lightweight, like uproot and flexible, such as boost histogram, than their root counterparts, which even though we might not have the exact same performance, is nice for people to get started right away and work even on their own personal machines. Additionally, Python packages often have a simpler implementation and a lower learning curve, which is great for getting students involved. And we know that students within these large collaborations is really the backbone and continues to drive the field. And so a recent survey found that about 50% of LHCb analyzers were using Python-based analysis code, which is great. And I'm sure this will continue to trend upwards. Additionally, many users often try to find alternatives for fitting procedures, but often tend to fall back to RootFit when other fitting tools aren't mature enough for non-trivial fits. So we need to consider that in development. Additionally, bootstrapping availability in the past was missing up until recently. However, now the resampling package has been added to scikit-hep, which has filled this hole. And additionally, now the architecture can still benefit a bit from a general purpose error propagation library and the Jacobi library, which will be discussed in this workshop, is been developed and hopefully will address this gap. Okay. All right, now I move on to the amplitude analyses and their tools in LHCb. So the amplitude analyses are the most computationally heavy analyses in the LHCb physics program. There's many tools available to try and fill this niche. However, today we're just going to focus on one, but I do want to say that there are many more on the market. There's tons of them out there, but today we'll focus on TensorFlow, which is an open source computing software which has been provided by Google, and it serves as a low-level library to provide the building blocks of the complex fitting procedure needed for amplitude analyses. Additionally, a number of institutes are making use of the GPU availabilities for fitting, DNNs, and amplitude analyses and these sort of things. And there is an additional potential to exploit the large LHCb HLT1 GPU farm outside of data taking to do these sort of things like very complex fits or DNNs or these large amplitude analyses. An additional Python package then making use of this is the Amplitude, which is a library of simple HEP applicable functions using the TF building blocks. And it gives a nice simplified class structure, which allows for accessibility to developers and application to other libraries, which is great. Okay. So the primary goal then that these analyzers want to share is that when a framework isn't always readily available, there needs to be an efficient computation with the trade-off between time to implement the code. And this is very, very important. And the processing time it saves when running. So just because the code is great and it processes things really, really fast, if it's a huge nightmare to get it set up and running, as analyzers, this now becomes a net loss over time. So additionally, there's frameworks like Zfit, which will be discussed at this workshop as well. They do it. Makes use of iMinWe for the minimization backend, TensorFlow backbone hidden from the users, and is quite flexible. So additionally, TensorFlow is heavy and not always hardware accessible. And so the community continues to look beyond TensorFlow. Things like JAX, PyTorch, etc. Are coming into the fold, and people are trying to make use of it. And this leads to the last point on the page. When developing code and frameworks using TensorFlow, developers need to try to keep it as a building block and not a cornerstone. What this then allows is to easily migrate to another computation engine in the future. So if you want to switch from TensorFlow to JAX to PyTorch, your code should be malleable enough where you can basically remove one block and put in a different block, and then allow things to proceed ahead. And this will allow, as newer, more powerful computational engines get developed in the future, you can take these and plug them right into your package. All right, and now I want to highlight just very briefly Zfit. There will be a larger presentation by Jonas, I think later in the week. So Zfit is a general purpose fitter, and it tries to harmonize workflows and include some advanced functionality beyond what is provided by the standard Python tools. So as stated before, it makes use of TensorFlow as a backend for parallelization and GPU support. But additionally, it makes use of uproot, boost histogram, and iminwe, which we've discussed earlier. And finally, it makes use of the HEP stats package, which is used in conjunction with Zfit for further statistical inferences. So currently, there are roughly about 100 users across LHCb and the Bell2 experiments making use of this package. And it has, it serves two primary analyses use cases. The first one being simple 1D mass bits. So the Pythonic package allows for easy implementation, very readable for newer and younger students that are just starting to get involved. And you can plug and play and get these things going for your simple 1D mass bits. And then on the complete opposite end of the spectrum, the next use is for extremely complicated fits. Because the package is extremely malleable, it makes for many fits possible, such as the matrix element for the B plus, the J psi phi K plus analysis, which is down here in the bottom. And you can see all of the complexity and different moving parts within this analysis that need to be fit together. And having such a malleable framework allows for these sort of things to be functioned. So some more feedback from the Zfit team. So the primary goal then, similar to what was coming out of the Amplitude Analysis people, is to have an accessible Pythonic fitting framework, which is beneficial both for new and experienced users. And they want this to be integrated well within the general Python data science ecosystem in general, and in more particular, the scikit-hep packages. So the team continues to further pursue integration for plotting routines and different statistical treatments, some with HEP stats, some standalone. However, at the time, there are still some PDFs which aren't supported. And when these aren't supported, that leads and opens up a potential for users to fall back to RootFit rather than trying to develop the PDF using TensorFlow. So the package would benefit greatly from additional support and feedback from stats experts. So fitting is a huge topic with many different avenues. There needs to be support from experts and the implementation of specific statistic recipes, either in the development or in the feedback form, to make sure that the statistical implementation is being done correctly. Okay, moving on now, I want to highlight the PID Caliph2, which is a package that is made use within the collaboration for particle identification and calibration. So this is a rootless particle ID efficiency estimation. And so here there's some software tools that are needed to extract PID calibration between data in Monte Carlo. And this primarily comes from the fact that PID is very tricky to model in LHCb, particularly because of the simulation of the rich. So having a data-driven correction of the simulated events using real signals is a great bonus. And to do this, they make use of a lot of Python packages. To start, running theme, uproot and boost histogram, simple access to root files with Python and subsequent histogramming, and additionally makes use of this higher dimensional binning, which was mentioned earlier. Additionally, then for plotting routines, we have matplotlib and a PLHEP. So this is a simple plotting, easy installation, very lightweight, and it additionally is great for LHCb people, where MPLHEP, you can apply your specific LHCb style file, but you also have the same thing for CMS and Atlas and these things available. And then finally, it makes use of the xrootd package for accessing remote root files with a Pythonic interface. Now, the framework or the data class used here is pandas. and it's used for manipulating tabular root data to vectorize the efficiency calibration. So there's a significant improvement over previous C++ iteration, primarily from the installation and overhead. And you can see here, again, making use of the nice matplotlib plots and the higher order histogramming. Sorry. Okay, so feedback again from the PID Caliph2 group. So the Python packages are simple to install and lightweight. This is great. This is great to ship to analyzers to use in the end product because they can install things and get things going right away. Additionally, using large data formats for centralized calibrations can become costly. So they want to continue to look for ways to cache between users to lower overhead and make use of some of these Python tools along the way. Additionally, as been mentioned, an event-by-event calculation is cumbersome, and there's a huge benefit to vectorization. So as developers within the Python community, and as you're putting together your package, there needs to try and be support for new users by sharing examples of how you can implement vectorization into their code, rather than using your standard event loop where you go over each individual event, where while it's simple and it's easy to understand, it isn't the best practice. So by having these examples of vectorization is great, and it helps new developers get involved and do things the right way. And then finally, of course, documentation is very good for some Python HEP packages and very poor for others. So even though there may be benefits of using these packages, the installation and implementation headaches don't outweigh these benefits, leading to a net loss and pushing people back towards some C++ methods. Okay, and now finally, I just want to highlight some of the additional tools utilized within LHCb, and I believe all three of these have or will be talked about within this workshop. The first one being Particle. Particle is a simple Pythonic interface for PDG information, and it's extremely handy for analyzers with many decays to consider in a single analysis. For example, within LHCb, some analyzers utilize over 100 individual PDG objects in a single analysis. So having a Pythonic interface to access the PDG information easily is great, rather than reading through the pages and trying to find all this info. Additionally, PyHEP has started to be used. So a new rare decay search is benefiting from the simple implementation to an ecosystem that normally doesn't use a lot of native his factory or his fitter or these sort of things. But by having this PyHEP as the Python interface to the HisFitter template builder, being independent of its root implementation is great. Additionally, and then finally, decay language. So a package for visualizing and manipulating decay chains with the Python tool. And it often is taking the .dec files. And for example, these are the basis of the LHCb Monte Carlo generation. So for analyzers within the collaboration, these are used a lot. And it can take these as input. Users can produce then simple but informative infographics like the one here below, describing their particle decays. For example, you have a D star, and you can see its different decay modes, and then even further down the line, the second order decays of the D plus pi 0. Okay, and now to sum up everything, I want to give some feedback from LHCb as both developers and users. First, we want to share we are developers. LHCb members play a big part in driving the developments of the HEP software ecosystem on many fronts, and not just users. And I can shout out some of the packages that have been discussed in this workshop: Particle, Decay Language, Zfit, I'm in We2, developed by people like Eduardo, Jonas, Hans, Michael, etc. All of these people are trying to lead the way in helping in this development. Additionally, developing the tools in-house allows them to be directly applied to analyses and other LHCb specific software tasks. However, there's still lots of room for more hands to get involved to try and generalize these things to the broader HEP ecosystem. Additionally, standard tools, your standard Python science package, tend to draw more interest, especially because of the application to life beyond academia. Many of our students are getting involved in HEP, but eyes forward to the future may not want to stay in academia and are looking for a step into the industrial field. So having access and training and experience with these standard tools is more appealing to them. Additionally, students are often learning Python tools in their university classes now. So the attraction to Python tools continues to grow and is great to see. And then finally, as feedback as developers, we want to encourage that people continue to strive for outreach and education, like is being done here, to try and get your packages into the hands of new users. You can have the best package out there. It can work great and perform at the highest level, but if people don't know about it, or people can't get it implemented into their code, okay, you've lost the interest of users. So you need to make sure that you carry on to the final step. And then additionally now, as users, our feedback is that it's very important that tools have relevant documentation, and there's huge advantage to accessibility if working examples exist as well, such as things like these Jupyter notebooks and things that people have been sharing this week. Additionally, availability of some testing tools is great, and the flexibility. So we know physics analyses and HEP analyses have lots of specific use cases. So having a test bed which shares a more wider scope is very valuable, rather than focusing on one specific type of example. And this is especially important for younger collaborators. Additionally, we do want to give feedback to the developers in the Python HEP community, because bug fixes when implemented are always done not always done, but often done quickly. And this is really encouraging and great for users. And then installation is quick and simple. This is a huge bonus over root software, which often takes a bit more to get things installed and get things running. By having this Python packages and being able to run them locally on your machine with a simple setup, just downloading Python 3 and pip installing whatever you want is wonderful. And then finally, new users can often be overwhelmed with the choice and struggle to know which tools to use. There's so many out there. So increased training, like at this workshop, and improved documentation can help these users to make informed choices on what they can apply to their analyses. So yeah, as a final conclusion, I just want to say there's a lot of advantage to using the scikit-hep and Python HEP tools. Please keep them coming. Thank you.
Thank you so much, Nate. So we have actually quite a lot of questions in Slido. So I would propose if you could take a couple of them, and then we, as usual, move discussion to Slack.
Okay.
Do you have a Slido link, or I will?
Yes, yeah, I have the link, but I'm not sure quite how the threading in Slido works. But
so
yeah,
Jim tried to help you.
Yeah, okay. So let's see. The first one here we have, you mean pandas data frames are preferred to our data frame. Despite the name, pandas data frames are very different things from our data frame. Both move to use. Okay, so I think Jim gave a good answer there. Yeah, so maybe I'll skip down to the ones that
yes, let's go there, and then we move to discussion.
And then, yeah, thanks. So you mentioned that additional computational backends beyond TensorFlow are considered. Which ones exist as usable alternative backends now? I believe JAX and PyTorch have been utilized within the collaboration. I don't know to what full extent, but these were the two that have been mentioned and were given as feedback. The next one, with GitLab CI, you mean unit tests or actually running the analysis? Even with tests, you might need access to data or Monte Carlo, so the data storage is proper. Yeah, so it's both of these things, right? So first of all, you can do unit tests. Generally, these are, you can make use of much smaller data files for unit tests, and these become simpler. But people now want to have this full analysis reproducibility within the GitLab CI. And so within there, with the LHC experiments, you know, the data files are huge. So there needs to be different ways to cache these things along the way, because you have many different steps and the data has many different iterations along the line as you manipulate it and do different things and get to your results. So it's both of these things. So in the current state, being able to run unit tests, I don't think is limited a bit by the data, because you can use a small file, but mainly stretching out to the full analysis. Okay, how is xroot-d used to read remote root files? How does it deserialize content of the file into memory processing? Unfortunately, I don't think I have the specific answer for that. I can find it for you and get it back to you, but yeah, off the top of my head, I don't have this information on the package. And then finally, is installation of these Python packages easier than root? Smaller, yes, but root is just a concurrent installation distance. Right, so root in itself has become a lot easier to install over than from when I got started in HEP 6 years ago or so. But yeah, it continues to try and to get caught up. But then as root is its own package, there are then many different things that are built on it. And then oftentimes you need things like CMake, this build procedure, all of these different steps, whereas the Python packages, you can install them locally to your machine, you get them right away. You then just import them directly at the top of your Python script. And this sort of feature comes back is quite simple, and especially for younger users who want to know actually or exactly what they're doing. Having this Python readability is a huge benefit where, okay, I know I'm using this package because I told Python I want to be using this package, and now I'm using this information, whereas root is this gigantic thing. You have to then worry about oftentimes if you want to use the compilation or these sort of things. So yeah, I mean, you can, of course, use root in Python itself, but then you have to try and find the different root classes, which can be quite cumbersome, whereas some of these different things with Python is nice to be able to pick out directly.
Nate, thank you so much. It was really nice motivation talk, and I hope everybody who has like follow-up questions, just go to Slack and let's keep on discussing